Welcome to the Toon Show. I'm your host, MC Toon. I love having fun promoting science and critical thinking. Often I do this by debating flat earthers on my YouTube channel, MC Toon Live. I also feature pre-recorded videos explaining science in an irreverent way on my Conspiracy Tunes channel. Jump on YouTube to see them and subscribe while you're there. And you can search YouTube, or they're linked on my website at mctoon.net. Today, I have an astronomer who's going to be talking about the sun and what we know about the sun. And I'll let him introduce himself. So take it away, Rob Parks.
Howdy, all. I am Dr. Rob Parks, or Professor Parks, PhD, if you follow me on YouTube. I am an assistant professor at George Mason University and also the deputy director of our in-house observatory, along with being our public outreach lead. My field of study, or my research interests, include young stars, essentially what we call young stellar objects, or YSOs, essentially how stars are actually forming disks around them, forming planets. I also am interested in the magnetic properties of stars. And then lastly, most of my observational experience has either been in photometry, which is studying the brightness of stars, or using interferometry, very much similar to how we acquired that image of the black hole in M87. I did the same type of an analogous procedure to get the first images of a star that was not our own or Betelgeuse. So that's basically me.
Ooh. Now you've said that word once, 2 more times, and he shows up. So be careful. So we're talking about the sun, the one that's the star that's closest to us, and a little more specifics of what we know about it and how we maybe know about it.
Well, we know quite a bit about the sun. Actually, it is, of all the stars in the universe, it is, as you might expect, the most well studied of all the stars. We have at least 2 satellites, more than likely more, that are solely dedicated to the study of the sun and various different wavelengths, so we can study various different physical mechanisms. We study the magnetic field of the sun. That is becoming much more of a pressing concern in terms of our development of, satellites, our development of exploring, space stations, going to the moon, that sort of thing. These things, solar weather is something that is becoming much more of a public interest topic. We actually have a small solar weather portion of our department, folks that are solely devoted to that. In terms of just bulk size, I apologize, I don't have the numbers memorized, but we do know the mass very well. We know the radius very well. We know the average magnetic strength of the sun very well. When it comes to one of the questions that I've gotten most is, how do we know the radius of the sun? And I can say that the first time we knew the radius of the sun, or the first time that we found it, was through the parallax of Venus's transit in the late 1800s. So what you can do is you look at the Venusian transit from one side of the Earth, and you look at the Venusian transit on the other side of the Earth, and what the 2 observers are going to see are different path lengths across the solar disk. And you can do the geometry. It's fairly simple. And from that, you can deduce a distance to Venus. And then from that, you can bootstrap your way to distance, not radius of the sun. I meant the distance to the sun. You can then bootstrap your way into a distance to the sun based on the Copernican ratios.
Okay, so it's about how long it takes to transit. And these were done for the same transit on different sides of the Earth.
Correct.
So we see Venus At nighttime, we see it either just after sunset or just before sunrise because of its angle to us. But in the middle of the day, when the sun's up, whenever it goes in front, and okay, interesting.
Yeah.
So that's the distance to it. And then we know the angular diameter,
correct,
which then gives us, we can then just use the angular size to tell us the actual size of it.
Yeah, one of my favorite astronomy labs that I taught back years ago, and I've been trying to find the same apparatus. In principle, it's a very simple apparatus. It's a high tripod, basically a telescope tripod, and on it is essentially a meter stick, maybe a little bit longer, and then two boards. The first board, or the board on the bottom end, is simply a screen. The board at the top end is a pinhole camera. And then you point it at the sun, you get an image of the sun on the back end. Very, very simple geometry. The ratio of the distance between the two plates and the diameter, the observed diameter, is equal to the ratio of the distance of the sun and the angular size of the sun. So, okay. Or I'm sorry, the distance of the sun and the linear size of the sun. So you can do a very simple measurement, and then you do have to assume one or the other. You have to either assume a distance or you have to assume a linear size of the sun. But in either case, you can get.
Yeah. Well, and when you say assume, it's not an assumption. It's based on previous measurements.
Yes.
Right. Yeah. So we can go to the other, the other methods for how the distances are measured.
Yeah. And it's a nice little also exercise in error propagation, because you have measurement error in your two measurements, and then you have measurement error in the value you look up. And then from that, you can, not only get a distance or a size, but you also know with what confidence you can trust that particular value.
Yeah. And yeah, error propagation is it's just not that often done. It's not easy to do. It's not sometimes intuitive when you're multiplying versus adding or dividing. When you divide something with, what do you do with the error when you're dividing it or multiplying? Or taking the logarithm or differential equations of it. Yeah.
More complex mathematical operations. Yeah, it starts getting a little hairy.
Yeah. But people know how to do it, and it's well explored in how to apply it.
Yeah, I have 2 books on error analysis, simply on data analysis, right over there. So
there are people that live and breathe that topic. So I like the geometry for the transit of Venus to get the distance to the sun takes several steps of geometry. Because I like a little simpler one. The amount of time that it takes to bounce radar off the sun, and people did bounce radar off the sun in the 50s and 60s. I don't know if they've done it since, really, but
I'm sure they've done it.
Well, it was really large arrays of antennas, and the amount of output of this was pretty strong. So there's probably some OSHA requirements or some FCC requirements that are now in place that might make it a little bit more difficult to do. But yeah, they bounced it off. It took about 980 seconds to go round trip, which knowing the speed of light in a vacuum, we now know from just that simple thing, right? That's really about middle school math to get that distance. So
a little bit of a funny story about observing the sun. I actually observed when I was in high school. I had access to the 40-foot radio telescope in Green Bank, which is still in operation for educational use. And my project was to figure out what the radio albedo for the moon is. And I had learned at that time that the sun, and this is technically true, that the sun is a radio quiet object. So I'm like, oh, okay, well, then I'm not going to get too much signal. So I look at the moon.
So can you tell us what radio quiet means?
So what radio quiet means is that it produces, in comparison to the rest of the overall energy distribution, how much energy is it putting out at all different wavelengths or what light it's putting out on all different wavelengths. It's very, very small. That ratio is very tiny. And also in comparison to other stars, because there are physical mechanisms that will make other stars louder in the radio than the sun is. So both in comparison to where most of the light is coming from, but also in comparison to stars that are of a similar type, but are more radio loud.
Okay.
So I first start off by looking at the full moon. And so this is an old chart reader. So I've got the pen, the moon comes in, it goes up, it's like a little tiny dip, and then it goes down. I'm like, oh, all right, yeah. I've looked at the moon in the radio. And then I tear that off around noon, I go back, and same thing with the chart reader. I get a lobe, like I get it high and I'm lobe, and I'm like, oh, all right, that's higher than on the moon. Higher than I would have expected, or smaller than I would have expected, but apparently the moon is the albedo is pretty high. And then as I'm thinking that, I see the needle rise. I'm like, oh, okay, that's weird, because at this point, little Rob doesn't know what radio lobes are, and so thing hits the top of the chart, stays there, and then this red light pops on. And I look, I'm like, oh, what is that overload? Okay. So I just start freaking out, like trying to shut everything down. I'm like, okay. So tip, don't even look at the sun using a radio telescope, let alone an optical telescope.
Yeah. Wow. So what frequency range was that at? Do you remember?
Oh, 21 centimeter, which is like 1457 gigahertz.
Okay.
I'm going to say. Something like that.
That's crazy.
At that point, it's funny. So with the electromagnetic spectrum, you can define it either by frequency or by wavelength. Because speed of light, they're equivalent, essentially inverse of each other. In radio, it's weird. In certain radio, we refer to the lines by centimeters or their wavelengths, and in certain ones, we refer to them by their frequency.
Yeah.
It really depends on what kind of astronomer you are. And then at the high end, it's either frequency or electron volts. So I'm like, all right. So our unit conversion in astronomy is a little bit, or our unit conventions in astronomy are a little all over the place.
Yeah. Electron volts instead of frequency or wavelength. Interesting.
Yeah. Essentially electron volt there. It's basically a energy.
Yeah. The Einstein-Planck equation.
Yeah.
So, okay. So, let's see, there was some more specific things we were wanting to talk about for the sun.
Mm-hmm. I mean, I can go off on any number of things with it. I can say that like one of the common questions that I've gotten is, how do we know that what the sun is made of?
Yeah. And
we know the sun is made up of primarily hydrogen and helium, which tracks because from other observations around in the universe, we know that the universe is primarily composed of hydrogen and helium. The Big Bang Theory gives us a very good explanation as to why it's primarily, when I say primarily, I mean around 75% hydrogen and plus isotopes and 24% helium. And then, as astronomers like to say, metals. Anything on the periodic table that has an atomic weight greater than helium, it's a metal to us. So oxygen, that's a metal.
I don't think so, but okay. You guys do that. Okay.
Yeah. Chemists I talk to kind of look at me like they're in pain when I tell them that.
I suppose when you look at the quantities of it, you're going to find metals are a large portion of the quantities.
Yeah.
Right.
I think it comes back down to, and this might seem a little bit counterintuitive, is that there is a lot of iron, or I say a lot, but a significantly detectable amount of iron in the atmosphere of the sun. And we also see iron fairly easily in other stars. And so when we talk about the quantity of heavy elements in a star, which leads us to an estimate of how evolved or how old it is.
Yeah.
We basically use iron as the benchmark, which obviously is a metal. And then we just kind of, everything else is sort of tied to that. Because if iron is of a certain proportion, then all the other elements are pretty much going to be of a certain proportion. So we kind of have a lazy approach to, hey, let's just use iron as the proxy and go from there.
Yeah. And so it bears explaining, why is iron the one? And I know there isn't iron. There aren't heavier elements in general in stars, at least being produced in stars normally. And so why is that the case then?
Why is there iron in the so if we look at the evolution of the universe, so just kind of skipping the back end, the front end, or the first parts, basically we had the first stars form. You have, like I said, you have primarily hydrogen, helium, and a little bit, tiny bit of lithium, and nothing else. These stars, when they formed, were huge. We're talking hundreds of times the mass of the sun, and they gravitationally contracted, formed stars that were very hot, very luminous, and they evolved very, very quickly. As we find with stars, they live, burn bright, die young. The more massive a star is, the more energy it puts out, and the quicker it runs through its nuclear fuel, and it ends. Excuse me. In the process of its formation, or in the process of its evolution, it's going to go through different stages of energy production. So initially, it's going to burn hydrogen and helium. Then it's going to go.
When you say burn,
oh, sorry.
Some people get confused.
Yes, I actually very recently had that problem. So when I say burn, what I mean is nuclear fusion. Is that you take, very roughly, you take 4 hydrogen atoms, slam them together, and in the back end, you get 2 hydrogen atoms that fly away, and you get a what we call an alpha particle, or a helium nucleus. And so from that, you get a tiny amount of energy because of E equals mc squared.
Yeah.
What we find is that if you look at the total amount of mass of the 4 hydrogen atoms, and really I should be more specific and say 4 protons, because at these temperatures, electrons don't stick to their nuclei.
They're just going wherever.
Yeah. So you've got the mass of 4 protons, and then at the back end, you can the mass of the 2 protons and the helium atom are slightly smaller, to the point that it is, I believe, 0.0007 percent. So it's a tiny, tiny fraction. I think that is. I believe that's correct.
But some small amount.
Very, very small amount. So any particular fusion is really not a lot of power, but you have 10 to the 20 or 10 to the 33rd kilograms of mass in the sun. So there's a lot of hydrogen smacking around. So ultimately it starts burning, or starts combining, and that little bit of energy from each particular thing adds up.
And the energy it outputs is in the form of photons.
Yes.
Primarily, there's
And I can go into why or how that energy goes from the core to the sun, because the entire sun is not. And I am going to default to burning because that's typically what I use.
That's fine. You've defined it now, so it's okay.
The entirety of the sun is not burning. The entirety of all of the nuclear energy really is coming from the inner 10% thereabouts of the core, or of the star, which is the core, and then it moves outward by 2 different mechanisms. But to go back, so it initially burns hydrogen to helium, and then in the core, and then it will burn helium into carbon, carbon into oxygen, silicon will get thrown in there, and then finally iron will be burned, or iron will be made. At this point, iron has a really cool property in that you can't fuse it and you can't fission it. You can't throw, if you throw two iron atoms together, if you could physically, which is kind of impossible, but if you could, the amount of energy that you would generate out of that is less than the amount of energy it takes to slime them together. Additionally, if you could somehow split the iron atom, again, you would get less energy out than it took to split it. So iron is kind of the stopping point from both the fission or the fusion kind of reactions and the fission reactions. So with a star is in what we call hydrostatic equilibrium. There are essentially only two pressures acting. You have gravitational pressure trying to bring this thing down to a point, really. And then you have some kind of pressure pushing outward. In this case, you have radiation pressure putting outward. The radiation pressure is basically the energy that is generated in the core and transmits through the star is keeping those outer layers afloat. And hydrostatic equilibrium means that, roughly speaking, the gravity and the radiation pressure are equal.
Yeah. Okay.
So when you get iron in the core, you can't burn it. You can't fuse it. So it loses that ability, that the radiation pressure drops because there's no longer any. There is still thermal pressure, but it's not enough to fight gravity.
So it gets distributed throughout the star. It's not just in the middle.
Well, it does. There is what we call dredge up, but that hasn't quite happened yet.
Okay.
Because right now, for these very early stars, it's pretty much in the core.
Okay.
And then because the gravity doesn't have anything really to in its weight class to keep it from collapsing, it's going to collapse very rapidly and blow up as a supernova. The supernova is incredibly hot. A supernova is the second most energetic phenomenon in the universe, aside from a gamma ray burst. And in there, that is where you get all of your most of your heavier elements, your golds, your silvers, your uranium. If you are wearing a gold band or have gold jewelry, there is a good chance, a decent chance, that gold was formed in the heart of a supernova. Most gold actually, as we find, is formed in another way, but that's another topic. Supernova, the gas gets blown out, including the iron that was created. That goes out into the universe or the galaxy, and then slowly that comes back down together. Gravity is always working, and then that forms new stars. And so, in this process, the iron from the previous star is now kind of can.
That's what's in the. That's what we're mostly seeing in the spectroscopy.
Yeah.
Okay.
And so that has happened 3 times that we know of. So we had the first stars, then we had the second generation of stars, which we call population 1. And then we have population 2 stars we call the first one population 2. It's counterintuitive. Population 2 and the current one's population 1. So the sun is a population 1 star.
Okay.
Means that it is fairly enriched, comparatively speaking. And so, yeah. And
are there any others that have been discovered that are population 0?
0. Well, there are new stars that are forming, these YSOs.
Yeah.
I think they're still getting lumped into population 1.
Okay.
I don't, at this point, the idea of creating a population 0 category, I don't think is
the numbering's all off. What are they going to do?
Yeah, exactly. I blame Hipparchus, really, with the whole stupid magnitude system. First magnitude is better than or brighter than 6 magnitude, so just throws the whole thing.
How do you do that?
Yeah. But in terms of how that iron gets distributed out, well, for the sun actually moves energy in 2 ways. It moves it through essentially a random walk process. Kind of think of it as you're at the bar and you need to go to the bathroom and you're really drunk. So you're going to plinko your way to the bathroom. So you're going to bounce off people next to you. And so since there are more people at the bar than there are presumably at the bathroom, the density gets less. And so fewer people you bounce off fewer people as you get closer to your goal. And ultimately, even though it's called random, because every interaction, every collision, as it were, of a photon with another particle is going to cause it to go in a random direction. Overall, it eventually, because there are less up here than there are down here, overall, it's going to migrate its way out.
Okay.
And that
so are these photons being absorbed by
in many cases, yes,
or just bounced?
So in many cases they're absorbed. In other cases they are scattered.
Okay, so they're absorbed and re-emitted, or scattered by just a bounce. Okay.
And so that happens over the course of about a couple million years. So a photon that is originally generated, that energy, or at least the remainders of that energy, are transported outward in about a couple million years in this process. That's when you get out to about 70% by volume of the sun. Then on top of that, you have a convective layer. And what that means is that the most efficient way of energy transport is no longer the random walk process, but actually boiling. So you have, in a simplistic way, you have parcels of gas near that boundary line, which we call the tachocline. We have that those blobs of gas, and they get heated more than the surrounding environment. And so very analogous to water boiling, that bubble is going to rise. And as it does so, it's a little bit leaky. And so it's going to be not brine leaky, but it's a little bit leaky. And so it's going to lose its energy as it travels upward. It's going to get to the surface of the photosphere. It's going to release what remaining energy that it really has until it equilibrium, or until it loses a little bit more energy than its surroundings. And then it's going to fall. And then it's going to basically do this. And this is what we mean by dredge up, is that heavier elements will find their way to the top of the radiative zone. You'll have that convective sail come up. Momentum will take it a little bit further into the sort of radiative zone, pick up some of these heavier elements, and then bring them to the top, and they'll get kind of distributed.
Okay. That's interesting. So now when you say gases, this is plasma, or are there actually gases with the electrons that haven't been disassociated?
There are, it's a mix. So if you're talking about but it is primarily atomic. So atomic gases.
Okay.
Because in this process, in order to get nuclear fusion happening, you need a temperature of 10 to 15 million Kelvin. The surface temperature of the sun is only 5880 Kelvin. And the reason for that is because every one of those interactions, the photon loses energy. And what I mean by the photon loses energy is that the photon gets absorbed and then gets re-emitted at a lower energy state. And actually, it emits a few different photons of lower energy than the one photon that got absorbed, because energy in has to equal energy out. But each individual photon has less energy, and it basically is at a lower temperature. And so eventually, you can think of it as the light cools as it moves outward, and then it gets to the surface.
Yeah, so the photons deep inside the sun would have a significantly higher frequency, gamma rays. And
the nuclear reaction is almost exclusively gamma rays.
Okay. But yeah, by the time it gets to the surface, it's visible light, which is significantly lower energy, lower frequency. Okay.
Yeah. So we see hydrogen, we see neutral hydrogen, we see iron. What really kind of trips me out is if you get to lower mass stars, you get cooler and cooler stars. And so at that point, the surface temperatures are so low that not only can you get molecules like water well, actually titanium, whatever, titanium, iridium, something of that nature. Titanium molecules, iridium molecules, these really heavy elements
in an actual bond.
In a bond. In the outer surface of the star, you can actually have molecules survive because the star is so cool at that point. And not only that, you can actually have dust in the really upper atmosphere because dust doesn't get destroyed, or certain dust doesn't get destroyed until the star about 1500 Kelvin.
Okay.
So yeah, so you can have dusty stars, which is just awesome to me.
So what's a sunspot then?
Sunspot. So the sun is magnetically active in comparison to other stars. There are some that are more active, and then there are some that obviously are pretty much not active at all. And so the way that it's generated basically is that through differential rotation. So you first start off, so the sun goes through magnetic cycles. At the very beginning of the cycle, the magnetic field is generated, and it's poloidal or a bar magnet. And that has to do with alignment of the magnetic moments of all of the stuff, or the plasma in the center. And so that so you get this nice bar magnet field. That bar magnet field will get frozen into the plasma, so that the magnetic field gets carried along with the plasma as it rotates. Now, if the sun were a solid body rotator, if it's rotated as a solid body, then you would basically still have a bar magnet very similar to the Earth. But the sun is not a solid body rotator in two very significant ways. One, if you were to observe the surface of the sun and you observe these sunspots, as Galileo did, you would see that sunspots at the equator or near the equator travel slower than stars near the top.
Oh.
Or I'm sorry, I'm getting things wrong today.
Other way around.
Stars at the equator travel faster than stars near the pole. And so when someone asks me what the rotational rate of the sun is, I'm like, on average, it's around 27 days. Near the equator, it can be as high as 20, or as short as 24. Near the poles, it can be as long as 30. And so you have this differential rotation. But on top of that, the entire convective cell, or the convective layer, where the convection is what's transporting that energy, that is rotating at a different rate than the radiation layer beneath it. So think of a ball where 30% of the volume is rotating independently or faster than the 70% inside.
Okay.
So, or in a really dumb analogy, the skin of a baseball is moving faster than basically the rubber bands that comprise it. Kind of in a way.
Yeah. Okay. So when we see sunspots, how long, say at the equator, how long does it take for a sunspot to move across our view of it?
So the rotation rate is roughly 24, 25 days. So if the sunspot lives long enough, then 12 days, something like basically 2 weeks.
Okay.
Thereabouts.
Because I have seen with the solar filter and a high zoom camera, I have seen sunspots and especially on the edge. You can see on the edge, like they're not the same shape. Because we're looking at them at a stronger angle there, so they're squished.
Foreshortened, as Wenbenga likes to say.
For sure. And they're taller than they are wide in our view of them, and kind of. Yeah. I don't know. I haven't looked at a whole lot of them, so I don't know a lot of the characteristics.
Yeah, as you go around a sphere, the foreshortening effect will change the position or shorten the position along that axis, whereas the perpendicular axis won't get touched.
Yeah.
So they say the same height generally as you move across, but their width will appear to get thinner.
So now, do sunspots, you said if they last long enough, do they tend to sometimes last long enough where it'll go around the back and then we see it come back around the front?
Occasionally, yes. So these are magnetic disturbances. So this cycle that I was talking about with all of this different kind of rotation, that magnetic field, like I said, is trapped in that plasma.
Yeah.
And so when you have all these different things rotating in different ways, it gets kinky. The magnetic field wraps around the sun, and you can have localized areas that the magnetic field basically flips back onto itself. And that magnetic field will rise up, because it's buoyant, it will rise up to the surface and it will impede the radiation beneath it. Sunspots appear dark because there is less light coming from that location than the surroundings, but they are not cold by any stretch of the imagination. Again, very similar to why you cannot see stars in the Apollo photos. When you are looking at a 4,000 Kelvin sunspot in comparison to roughly a 6,000 Kelvin surrounding surface, it's going to appear black. But if you were to pluck that spot off and stick it in the sky, it would shine like a star.
Yeah. Okay.
And that magnetic disturbance that creates that is somewhat chaotic. And so sunspots only last anywhere from days to weeks, maybe a month or so.
Okay. And they name them and number them, right?
Yes.
I've seen pictures of stars with like a sunspot and then there's like a little name next to it.
Mm-hmm.
A number usually.
Really, they're just differentiating because again, this is chaotic. And when I was talking about on average, the height, sunspots, or mainly sunspot groups, because it's rare. Most sunspots that are noticeable, when you look at them, you're actually not really looking at a single spot. You're actually looking at many different spots that are tight together. And because of the angular resolution, they may appear as one.
Okay.
And so what they're labeling is the name, that is the sunspot group, and then the individual spots get numbered.
Okay. All right.
Because, and I don't know why it's done this way, but sunspot number, which has been tracked for centuries at this point, is a great indicator of how active the sun is. And the way that you do that, or the numbering, is not just counting them up as you might expect. It's actually called a Wolf number, which is the number of, you multiply 10 plus the number of 10 times the number of groups plus the number of individual spots that you can see.
Okay, so it's not a sequential number. There could be a repeat of the same number. Okay.
Yeah.
I got it. Okay, that's interesting.
And they've been, the observatory that I did my thesis at, they have a 150-foot solar telescope on Mount Wilson, and so they have the longest continuous ground-based record of sunspot numbers. So if you were to go there, and they have tours, you can go in there, and they have a ginormous table that's essentially the length and width, or length of a pool table squared. It has a giant image of the sun, and they literally stare at it and be like, "Oh, spots," and they count it up every day.
Wow.
Solar astronomers are a little weird. But so obviously we have satellites to do that now, but they've been doing it, like I said, since I think Mount Wilson was built around 1920.
Yeah. Wow. How big is that telescope?
It is 100, and so with solar telescope, you're talking about the focal length. So the focal length is 150 foot. So it looks like a tower. So you have a telescope or you have a collecting mirror at the top, which I don't remember the aperture of. It's at the top. It redirects that light downward, and that focal length is 150 foot.
Okay.
So if you were to Google it, it kind of looks like a water tower with a pipe down the center of it.
Okay. So a little different than a big telescope that's got just a big circle that's pointing at stars and stuff. Okay.
Yeah. I mean, it does have a mirror to reflect the light, but it's definitely a different optical design.
Yeah. Okay. That's pretty cool. Okay.
Yeah.
So now I bring up that radar has bounced off the sun. Some people say, well, the sun is a black body. Can you, yeah, sort of, right? Can you explain what's meant when people say the sun is a black body emitter or black body radiator?
Sure. A black body, strictly speaking, is any object that radiates away the same amount of energy that it receives in exactly the same wavelengths. So if you looked at the amount of energy as a function of wavelength, and you measured the intensity of that light over wavelength, you get what we call a Planck curve or a black body curve. And that curve tells you some very fundamental things about the object. If you take the area underneath that curve, you now have the total luminosity of the object. If you look at the peak of that curve, you now have the temperature of the object. And so different temperatures, the curve is going to get smaller at lower temperatures and get larger at higher temperatures. And that peak is going to shift. But that is a first order simplification. If you look at stars, and this gets worse as you go to those fainter or those dimmer stars that have all those molecules, you have, in reality, the sun it produces an absorption spectrum. So that black body curve, that is also referred to as a continuous spectrum. There are no sudden deviations off that curve. So if that's the equivalent of a rainbow pattern of color as seen through a prism. Now, Newton was the first person to do this. Fraunhofer was the first person to do this with any kind of precision. He took sunlight, passed it through a rudimentary spectrograph, and he looked at the light, and it was a rainbow pattern of color, but superimposed were these dark bands. And those dark bands correspond to particular atoms, as we were talking about before, as you pointed out before. Atoms, when photons hit them, if the photon is of the right energy, it's going to hit the atom, and the atom's going to suck up that energy, and it's going to re-radiate it in some random direction. And so when we look at the surface of the sun, some of that light has gotten absorbed by those elements and re-radiated somewhere else, typically as a different wavelength or different energy. So you have these dark lines superimposed. Now, if you go to the graph of that curve that I was showing, what that shows is, you're going to have these dips through it. And we refer to that in astronomy as line blanketing. And what that means is that in certain wavelengths, again, the line looks dark because it is literally colder. There's literally less energy there. And because, as I said, the sun is in hydrostatic equilibrium, the amount of energy it generates has to equal the amount of energy that it radiates, or it's going to expand and explode. So that energy that is being inhibited by those particular elements has to go somewhere. And so what that'll do is, in certain parts of that curve, it'll actually raise that up. So so in the sun, because of all those hydrogen lines, it might produce a little bit more in the X-rays than if it were truly a black body. Does that make sense?
Right. Yes. And so none of that is about whether or not it can or cannot reflect things.
No.
Right? That's about emission.
Yes, it is emission. The sun doesn't reflect anything. It just emits energy, absorbs.
Well, except when radars bounce off of it.
Oh, well, yes. Oh, I'm sorry.
How does then radar bounce off of it if it doesn't reflect?
So, the way that I would look at it is, so light is the radio photons are streaming out. They smack into that sun. Those radio photons will get absorbed and then re-emitted And some of them will be of the same energy. Some of those photons will be of the same energy that it received, and some of those will be bounced back or will be shot backwards. So when I think of reflection, I think of it in sort of the geometric optical terms of a light ray hitting a surface and then coming back out. But in actual terms, what's happening is absorption and re-emission. Is that the incoming photon gets hit, it gets absorbed by an element, and then gets re-emitted back into your line of sight, which is why the reflected signal is one of the reasons why the reflected signal is always so much less power than the transmitting signal.
Yes. Yeah, and they needed an awfully large signal to let's see if I remember, 500 kilowatts.
Yeah, I don't doubt it. That has nothing to do with so line blanketing. No, it's completely independent. The reflection is simply that there are physical atoms there that are collecting the light and re-emitting the light.
Yeah. All right. So how long do we have? So the sun now is in equilibrium, but there's a certain amount of fuel, as you said, that's burning, and at some point it'll be gone. Then what? How long?
Yeah. So just reminds me of I was talking about something very similar to this. Actually, they brought it up on Tartaria's Discord, not to keep advertising them. Might have been Earth Awakenings, either one. The conversation went from normalish to all caps ranting in less than 10 minutes, which for me is a personal best. And he just kept posting like SpongeBob going, the sun's going to die in 5 billion years. We're all, okay. So to answer your question, the sun actually is getting ever so larger, even as we speak. It is that that nuclear fusion that happens is very, very temperature dependent. And so as that process goes on, that process will heat the core ever so slightly, and then the nuclear energy generation rate will skyrocket, will go up very, very quickly, which will then make the temperature go up. And that causes a feedback cycle. Yeah. So the sun is getting ever so slightly larger, ever so slightly more luminous. So in terms of us, we need to get off this rock in about 1 billion years, because at 1 billion years, the oceans will boil and the earth will in no way be habitable unless we want to dig. And then about 3 billion years after that, the sun's radius will get so large that it will probably encompass the earth. If not, there's going to be so much drag on the earth from the solar winds at that point that it will just degrade and get thrown into the sun. And the reason for that, briefly speaking, is that the sun will evolve into different stages. Right now, we call it a main sequence star or an adult star. And then the next step is into a red giant. And the reason for that is because of the way the energy is being generated in the core or in the interior. The energy in the core, or the core now is in that stage, the core is inert. It's not burning anything, but there's a shell of hydrogen burning around it. And that actually is producing more energy than the core burning before it. More energy, more radiation pressure.
Yeah, makes it bigger. All right, so in the very center, that's where it's primarily helium. It's already done its fusing.
Oh, when it's done fusing, yeah. So in the red giant phase, yes, we refer to that as an inert helium core.
Okay.
And then you have a layer or a shell of hydrogen burning into helium around it. And then that
moving
helium
outward as it does that.
Well, it will eventually stabilize. It will essentially, the core, when the core stops burning, when it produces energy, stops producing radiation pressure, it's going to contract. And as it does so, all of the rest of the stuff is going to contract with it. Gravity is inverse square law. So the stuff nearer the core is going to contract faster than the stuff further away. And that is going to get into a temperature range. That helium that was above the core is going to shrink down, heat up to a point where it's at 10, 15 million Kelvin, and it's going to start burning into helium, just like the core did.
Well, no, the helium fuses into...
Hydrogen fuses into helium in that shell. The helium stays helium during this entire process. During the red giant phase, it doesn't burn at all.
Okay, but after that phase,
you have what's called a helium flash. Essentially, the pressure, helium. So the way nuclear fusion works, roughly, is you have two atoms. They're surrounded by electrons. If you bring them together, electrostatics is going to say, nope, they can't marry and have kids. But if you throw them together fast enough, then their momentum essentially carries them close enough before electrostatics can, split them apart, such that the strong force will bind them together, and then they combine. The core during the red giant phase is still cold enough that the atoms are not moving fast enough. Electrostatics still manages to cause things to fly away. But in this process, the hydrogen is still burning helium above it. That helium, because again, gravity goes down, you get more and more helium, the pressure gets higher and higher until it finally can't take it anymore. And those helium atoms finally get smashed into each other and stick. And then you have what's called a helium flash that causes the core to immediately ignite from helium into carbon burning. And that causes the star to expand even further out.
So helium to carbon, because there's 2 protons in helium and how many in carbon?
It's a little bit more complicated. So
yeah, okay.
My inner 5-year-old is going to chuckle at this. The process via which the hydrogen fuses is called the proton-proton chain, or the PP chain. The process via which you get hydrogen into carbon is called the CNO cycle, which is the carbon, nitrogen, oxygen cycle. And so it goes basically the oxygen and nitrogen act as catalysts. And so it goes through more steps, and beryllium gets created in this process. And so it's called the carbon, but there's a bunch of other stuff that gets created in the process. Okay. And then ultimately it's going to, the helium is going to burn into carbon. And then you're going to have, again, a situation where the core runs out of nuclear fuel. It's an inert carbon core surrounded by a shell of helium and helium burning, then an outer shell of hydrogen burning. The star is ginormous at this point. It's going to be larger than the orbit of Mars. And then we run into the issue of, while the sun just doesn't have enough mass, gravity really doesn't have enough gravity doesn't have enough oomph to compress this thing down any further. But what is happening in the outsides is you have radically changing temperatures, you have radically changing densities and things of that nature. And so the star pulsates violently, and it will blow off its outer layers.
And we see this now. This isn't just guessing. We see this in stars currently.
Oh, yeah. The way that we see this is this process takes billions of years, or in this case, millions of years. So obviously, we're not looking at a star and watching it do this. What we're doing is we're looking at thousands of stars, and we're seeing that some of them are now had this shell of material around.
Different ages of their development.
Exactly.
Okay.
And that is called a planetary nebula, which again, in astronomy, has nothing to do with planets. It was called that by William Herschel, who was like, all right, with my telescopes, the only things that look like disks are planets. I know it's gas, I know it's not a planet, but I'm going to call it a planetary nebula because it looks like a disk. So, and we stuck it.
All right. So, all right. So back to it. It's in this phase where it's burning multiple layers. Gravity is trying to do stuff. It sheds off in these different pulses. Mm-hmm. So it's kicking off material.
Yeah.
Through this bouncing due to gravity and radiative pressure that's going. It's not in equilibrium anymore.
It's no longer in hydrostatic equilibrium. Is that and so it really has to do with things like opacity. In that, how easy is it for that energy to get out? And so, in these later stages, particularly the outer envelope, what's happening is that there's going to be regions where the energy just can't pass through it. It's the opacity, the thickness of the layer. It's kind of like a thick fog. Light can't go through it. And so it's going to get trapped underneath those layers, and it's going to push those layers up. The opacity or the thickness of the fog is going to dissipate or lower. That light will then basically go out and carry material along with it. And then the rest of it will settle down. The opacity gets thicker. Cycle repeats.
What's the time frame of these types of cycles? Days,
thousands of years. Thousands of years, I think.
Thousands of years between each burst.
I would think so. Okay. This is in an area that
little outside.
Well, no, it's an area that I don't think is very well studied because, again, it's so when you look at stellar evolution, things either happen very slowly or very quickly. And so the idea is, because again, we're looking at all these stars, if something is happening very slowly, when you look at a group of stars, you're going to see majority of them in that slow process.
Yeah.
So if it takes 1 billion years to do something, you're going to likely find that all those stars fall into that 1 billion year time frame. But if something happens on the order of 10,000 years, you have to be lucky. You have to luck out and see that object in that small time window.
Yeah.
And so in these phases, there's just not a lot of objects for us to find. And so it's hard for us to have like real observational fence posts to be able to answer that question. So
okay. That's different than things like is it Cepheid stars? Like Polaris has a
Cepheid stars. Yes.
Cepheid. Oh, I always say Cephids. It wrong.
So that same process that I was talking about before, or Cephids, if you pronounce it that way. Stars go through instability, and they can come out of it. They can actually go through this, what we call the instability strip, multiple times as it evolves. But it's not catastrophic at this point. The layer that is causing the opacity is further down, so there's enough mass on the top that it doesn't get blown out. But what's happening is, again, the energy is getting trapped. It'll blow the SAR up. The opacity or the transparency will go down. The energy is able to be released. The star collapses. The process repeats itself. And so that's actually one of the ways we know distance to stars, is that Henrietta Leavitt, one of the computers working at Harvard Observatory in the early 1900s, she looked at thousands, millions, really, or hundreds of thousands of stars, and she was able to piece together that if you looked at the essentially the innate brightness of the star, and you looked at how long it took to pulsate, the period of that pulsation, they were correlated. And so with distance, or when you look at the brightness of something, there are really only two factors that are in play. First order, how intrinsically bright it is and how far away it is.
Yeah.
So you can imagine if you put a flood lamp and a candle right next to you, obviously the flood lamp's going to be blinding. But you can imagine if you push the flood lamp far enough back, that the light from the two will eventually become equal. So if you know from the period luminosity relationship, if you know what the period is, if you can directly observe the period, You can then, from that relationship that Leavitt found, you now know the intrinsic brightness. And so you compare that to the average brightness that you see it. And so now what's left is distance.
Yep. Yeah. So I had Eric Burns on a couple of weeks ago, and he's just finishing his master's in astronomy, or he says it's all physics. Your major is actually physics, right?
Essentially, yeah.
Yeah. So he covered multiple different ways that we are able to measure the distance to stars.
Mm-hmm.
So, and he contacted me. He wants to come on again. He has some other topics he wants to cover as his finals wrap up.
Nice.
And between his master's program and his PhD program, he's got a little time. So I'm looking forward to having him back on to cover some of these things.
Do you know where he's getting he's doing his thesis?
I don't remember.
Okay.
But yeah, I think
I'd be interested. He might be working with somebody I know.
It's a good chance. It's not a small community, but there's enough that you might know each other well enough.
Yeah.
Right.
There are communities within communities. So if the person he's working with works in interferometry or works in young stellar objects, then more than likely not that I know the person or have at least heard of the person. If they're an X-ray astronomer, chances are I don't know them.
Okay. All right. Well, anything else that you had in mind that we should include?
Let's see. All right. So the last, there is one last thing I want to talk about is this idea of how old is the sun? Like, I talk about things going 4.5 billion years, blah, blah, blah. That was actually very open. And that was one of the ways that we nailed down what was happening inside the star, how the star was generating its energy. Because very early on, when we're talking like the early 1800s or prior to the mid 1800s, there was this idea that it was literally burning. Very much like Aristarchus in the past, who thought it was a burning rock. There were folks who was like, all right, this is a chemical fire in space. And then later, but if you actually do a very back of the envelope calculation, what you would find is given the mass or given the amount of material and given the efficiency of burning of a chemical fire, then you would you would burn through the sun on the order of 10,000 years. Now, two gentlemen by the name of Kelvin and Helmholtz came by and it's like, okay, well, we know that the Earth is billions of years old, so obviously it can't be a chemical fire. So what about contraction? Because if you cause something to contract, you're converting gravitational potential energy into kinetic energy or heat. And so they're like, well, what if it's that? What if the energy that we're seeing is the energy generated when it collapsed? And so they did the same kind of back of the envelope calculation, and they came up with about 250 million years. And they're like, nope, that's not it either. That might be a contributing factor, but that's not it either. And then it was only until the early 1900s when basically Niels Bohr and the nuclear physicists came together and basically said nuclear fusion is a thing. They then did the same calculation. It was like, wait a minute, okay, if you do that for the sun, you get a lifespan of 10 billion years, roughly speaking. Like, hey, and that fits all the other sort of observations we're seeing. So that's kind of how we know.
Yeah. So Occam's razor says that's a good thing to investigate. Let's go that direction.
Exactly.
Very
I
good.
am occasionally, I even when I was saying this, the thing that occurs to me is, something is simple. Well, something is taken for granted as what is causing the sun to burn, nuclear fusion. We've only really known that for about 120 years. Mm-hmm. In the span of, astronomical knowledge, that's nothing really. And so it amazes me that a lot of the astronomy that I teach today, we've only really discovered within the last century or even couple decades.
Yeah.
So it's really exciting.
It's interesting that it took. I mean, it makes sense that Bohr is the one who first proposed the Bohr model, right, of the atom, whereas it wasn't just one thing, but it was a core and a nucleus with electrons moving around it. Of course, what was that, 11 years, all of 11 years or something like that before the Bohr model was replaced with some, a more accurate.
Yeah. Quantum mechanicals.
But it was a revolutionary idea. And his idea of that really just, I think it sparked so many different things that it unlocked the door for understanding how sun works, as well as tons of stuff in chemistry and biology eventually. And
and the Bohr model is yet another example of the idea of, folks are confused as to classical mechanics versus relativity. The Bohr model is not factually is not accurate to reality. We know that electrons are not orbiting in orbits in a flat plane, but it's still useful as a mathematical tool. If you want to know what the energy is that a hydrogen atom generates when an electron moves in different shells or orbitals, Bohr model will give you that answer.
Yeah, it's a great way to think about it.
Yeah.
It's a simplification.
Yeah. It's a tool. It's a practical, useful tool. So why get rid of it?
Yeah.
I mean, if you want to do a full quantum mechanical treatment, go nuts. But why?
You'll get the same answer depending on the amount of precision you need.
Yeah, exactly. Yeah. It's just harder and more complicated. So why do that to yourself?
Yes, if you don't need. Well, Rob Parks, it's been a good conversation. I've enjoyed this. How can people who are curious find you? I'll whatever you have, I'll put in the description of the podcast.
So my YouTube channel is Professor Parks PhD, and most of my content is basically are my lectures that I give here at George Mason. I am right now finishing up a little bit more in-depth lecture series on the solar system. I will then transition to extragalactic astronomy. And then on top of that, I will actually start doing some algebra-based physics courses or lectures. So, and then I also have little bits about flat Earth and stuff like that. So,
refuting flat Earth.
Yeah.
At some point, you'd think the flat earthers would say, wait a second, we don't have any flat Earth astronomers that are answering the questions about how the sun works.
Yeah.
None of them can even have a consistent proposal for how the sun works.
I only know of one prominent astronomer who is actually a young Earth creationist. And the gymnast, well, he only has one gymnastics flip that he has to go through. God made it that way. But even he, in his very small astronomy textbook, I think it's the third section, like not chapter, section, Earth is round. Like he explicitly states, he has to explicitly state that while I believe the universe is only 10,000 years old, the Earth is round. So even the young Earth creationists really don't believe the Earth is flat.
Yeah.
So,
I had on Dr. Danny Faulkner, who is a young Earth creationist and an astronomer.
Oh,
just 2 weeks ago, and
I will have to watch that.
I do not agree with the age of the universe stuff, but as far as the astronomy went, I could, to me, from my non-astronomy background, it seemed spot on. And some people are like, well, he's a young earther, but nobody said, well, he was wrong on the other stuff. So take it what you will. I think it's good to include different opinions.
I don't, with Dr. Lyle, the thing that really struck me is that he got his PhD on looking at the magnetic field of the sun. So he is very well aware of how the sun generates energy, how it generates a magnetic field, and that has to take billions of years.
Yeah.
So again, the one flip that he does is that God made it look that way.
Yeah, which some people call last Thursdayism, which is the universe came into existence last Thursday, and all of our memories and everything in motion of the entire universe also was put into place last Thursday at the same time.
Yep.
So, all right. Well, thank you. Thank you very much for talking with me today.
I'll give you the link to my YouTube channel. Yeah,
absolutely. Yes. I'll be sure to have it in the description on the podcast and on YouTube. So thank you everybody for joining us today. If you want to see this podcast as a video or to participate in a conversation about it, you can find it on YouTube. Search for Toon Show. And if you like this podcast and want to support it, head to patreon.com/MCToon. We'll see you next time.